Welcome everybody to maybe our last day of talking about binary search trees. So today we are going to learn how to debug them. I've written some code and I've deliberately introduced bugs into it. See if you guys believe me on that one. So, but yeah, seriously, I was just a second ago deleting code out of it to make sure that it segfaults. And so when we go ahead and compile it, it should compile just fine. So here we have a binary search tree implementation. So we're going to be doing something called black box debugging, which means you don't have access to the source code, but maybe you can run the program, and based on the behavior of the program, maybe you can figure out what the code is actually doing wrong. Okay, so give me some operations. Right now we got an empty tree. What kinds of things should we do? Just type things out in the chat. I'll punch them in, and then we'll see if it works the way we expect it to. Okay, try to print. All right, nothing. Seems fine. Okay, no segfault there. Insert 5 and segfault. That seems like a problem. So what was our test case to cause it to segfault? Inserting anything. All right, so what function? Let's try deleting something. Segfault. Let's try searching for something. Segfault. Looks like we're segfaulting on everything. So what do you think is causing this? What do you think would cause it to segfault on an empty tree? What happens when a tree is empty? Does the something not exist? Nothing exists. When we start off, there is no tree. So here, we are searching the tree. This is the code that I gave you guys on Wednesday of last week. Contains, and I gave you two hints here. First, check to see if the tree is empty. And then if it's not empty, then recursively call into root.contains. Okay. And what if I just happen to have forgotten to put that there? Now, why would contains segfaulting? Like, I think you guys can all see that, right? If root is null, doing 0 points to something is a dereference. It's a null pointer dereference. Brett the Hitman Heart comes out and attacks you. What do I need to put in here into contains? But why do you think, at a higher level, why do you think this is causing insert and delete to crash? What do we need to put in here? If we're searching on an empty tree, what should we do? Is 50 in this tree? What should we do? What should we return? Yeah, so if root is null, then return false. So, yeah, so that's in there. And so let's save that. And maybe try inserting the number 1 now. Oh, look, it inserted now. How did fixing insert 2, insert 3, insert 4, how did fixing contains, oh, but it's not working right, I don't think. Insert 4, print, it's not printing right. So, but it's not segfaulting. So why do you think fixing contains fixed insert and delete's probably gonna, no, segfault? So how did fixing contains fix insert as well? What do you guys think? Without looking at the code, what do you think insert is doing? And why? So just fix contains, and insert stops segfaulting on an empty tree. It's a logical connection here. Insert must call contains somehow. Yeah, exactly. Very good. So what is happening in insert is that, that's the recursive version, is that it is starting off by just checking for duplicate. So if there's a duplicate, return. And so it was calling contains to see if the thing's in there. And if it was in there already, just return. Okay. So insert was calling contains, and erase, delete, is also calling contains. That's why that one was segfaulting as well. It was because if you're erasing something from a tree that's not in there, you can just return. You don't have to do anything. Okay. So, good. Do you see, Luke, how you can like kind of guess what the source code looks like just from running it? You're like, I think you can figure out what's going on here. Interesting. So why is, okay, so let's do this. So if we insert 42 and we print it, it works. But if we insert 100 and print it, we get 100. What's going on here? And if we insert 200 and print it, we get 200. What happened to the other numbers? What's going on here? What do you guys think? Discuss. All right, so every time I insert, that new number is the entire tree. And so we've got different hypotheses here on chat. I paused the recording for a little bit. Marsh, maybe they're getting deleted. Numbers are not saving. If it's only showing a single number, it might be because size is staying at 1, or root is always being redefined. Yeah. So let's take a look at insert. Here's our code. So if we have a duplicate, we return. So that might be a problem, right? Like maybe it's falsely returning it's a duplicate every time and quitting, except it's not because it's changing the number. So that can't be it. It's not just returning without doing anything. So if not size or not root, root is equal to a new node. Otherwise, insert the new node into root. So what do you think is happening here? Are we, with this insert function, maintaining our class invariance? You guys remember the class invariance up here? Size must always contain the number of nodes in the tree. Everybody to the left should be smaller than me. Everybody to the right should be bigger than me. No duplicates. And if a tree contains no data, root is null pointer. Are we maintaining all of those invariants, or did we forget one of them? That is correct. We forgot to increase the size of the tree. So every time we come in here, size is still 0. And so it keeps doing this highlighted line over and over again. Every time we insert, root becomes the new node is the root. It just keeps leaking the memory for the old ones, just replacing the old tree every time. So what do we need in here? What do we need in here? How do we fix this? What do we do? Size plus plus. What if I put it here? Is that all good to you, Burford? Size plus plus right there. Is that going to fix it? Remember, it's not size or not root. So we actually didn't shoot her. Like you guys all thought that it was going to, basically work like this, right? If we had it like that, then yeah, it would segfault. Got some news. Yeah. It's segfaulting because by incrementing the size first, then it's doing this line and segfaulting immediately. So we'd have to put the size plus plus down here for that to work, right? Yep. Or we just say if root equals null pointer, or we just say if not root. Either way will work. Okay. Probably if not root's the way I would do it, because you always want to check for root being null before you dereference root. This is just good coding pattern. Every time you use a pointer, there's always a possibility that pointer is null, and you need to handle it. Okay. So now it should work. Maybe. Insert 1, insert 2, insert 3, insert 4, print 1, 2, 3, 4. Seems fine. Search for 2. Search for 111. All right. Are we good? Are we good to go? What do you guys think? We've made a binary tree 1, 2, 3, 4. Are we good? Have we tested it fully? Are you happy with this? What about delete? Yeah, huh. Yeah, test delete, test the edge case. All right. Well, let's test delete. So let's delete 4. That's the very bottom one. Oh, seg fault. All right. So which line of code did it seg fault on? The last one, right? So maybe that's just, insert 2, insert 3, insert 4. Let's delete 1. Oh, also seg fault. Insert 1, insert 2, insert 3, insert 4, delete 2. That one worked. But the tree's messed up. There's nothing left in the tree. The tree's empty now. So there's something seriously wrong with this delete function. Yep. So let's take a look at it. And we can take a look at it, or would it be more useful to just know which line of code it's dying on? What do you guys think? Would you guys like to see where it's dying? Now we could do something like this, right? Like we could do like, cout A, cout B. That's gonna get kind of tedious. Okay, so let's do this instead. G++ -g. And we're gonna go gdb a.out, and we're gonna hit run, and thread debugging. Okay. We're gonna insert 1, insert 2, insert 3, insert 4, print. Got everything in there. Let's delete 4. Crash. Okay. Now, when your code crashes inside of GDB, it will show you where it crashed. It crashed on line 97 of main.cc. Very useful. Okay. And see if I can get the sim. Yeah, okay. Okay, whatever. So backtrace. Okay. So we are on line 97 of main.cc, which was called from 196 of main.cc. Okay. So let's see here. Just gonna leave that open in the background. Main.cc line 97. If you put a plus there, we'll open up on line 97. So this is the crash. While temp, if temp points to data equals t. That's an interesting crash. Because it says while temp is not null, temp points to data, if temp points to data equals t. Print temp. So temp is not null. Print t. T is 4, right? Because we're erasing 4. Print temp points to data. Cannot access memory there. So we're accessing memory that's been deleted. All right. Interesting. So we've deleted temp, and then we're trying to access its memory after it's been deleted. Interesting. How could this be? So we got a while loop here. And then here we're deleting temp. And then we come to the bottom here. And then we come right back up to the top. After we delete temp, probably what should we do? We just finished. What should we do? It's pointing to temp even after we delete it. Remember when you delete a pointer, it doesn't set that pointer to null. When you have a lot of students have trouble with this in particular. Like, let's say that you've got temp, right? And we say delete temp, and then we say temp is equal to null. A lot of students say that's going to segfault. Wrong. The reason why it's wrong is because temp is like an integer. It's literally just an integer under the hood, and you can set an integer to 0. That's not using the memory at root, at null, rather. It's setting the pointer to hold the memory address 0, which is fine. You can always do this. Okay. Now, I didn't set temp to null here. I could say temp equals null. I can say temp equals 0. Or I can say temp equals null pointer. It's all the same thing. And then it will messing with the size is going to be the hard part, right? So maybe maybe we can just do this. We'll just assume that size gets decremented. I don't think we can use size anywhere else in here. Yeah, okay. So we'll just always decrement size and just hope that it doesn't come up again. Okay. So what's happening here is we're deleting temp, and then because we didn't set temp to null pointer, which doesn't matter, it came back up here. Hey, temp's still not null. It dereferenced it, segfault. That's why our code was crashing. And we're doing this a lot. So instead of doing all that, we should probably just return. Right, we're done. We deleted the node that we're trying to delete. And we could set it to null pointer, but we could just return. Like, we're done. We've deleted the thing we're trying to delete. And so let's talk a little bit about delete today. So there's a number of test cases, a number of test cases, a number of possibilities you have to handle when deleting. Deleting is an annoying function. Okay. So the first thing that I check for is the thing in the tree? This just makes all of our logic a lot easier. We don't have to worry about the case where you're trying to delete and you get to a null pointer and you're like, oh, it's not there, return. So the first thing I do is I just say, hey, if you're telling me to delete the number 50, I first check to see if 50 is in there. If it does not contain 50, so that says there, if it does not contain 50, return. We don't have to do anything. Is it inefficient? Sure, we're probably doing twice the work we're supposed to, but it just makes all of my cases a little bit simpler down below. Okay. I don't need to echo size. Now, the first case we have to handle is you're deleting from a tree that has one element in it. And we know that it matches now, right? Because once you get past this, you know that the tree has elements in it because the tree is empty, it would return false. So you know root's not null. That's nice. This one line of code highlighted here does a lot of work for you. It does a lot of heavy lifting. That's why I like it. So if we make it past this line of code, we know that root is not null. We know that there's a tree. We don't have to check for a null pointer. And we also know that there is at least one element in it. So we don't have to worry about that case either. Okay. And we know that T is in it. So we know that we're going to have a match. See here, if there's only one person in the tree, we can just delete it. We don't even have to check to see if it matches because we know it matches. It's in the tree and it's the only one. So if we are the only person in the tree, we're going to delete the root, set root to null, because that's one of the invariants, right? We're going to set size to 0 and return. You guys understand this right here? So if we're deleting from a tree that has one element in it, then we set root to null. It's the only time that root's ever going to set to null. So if we have a situation like this, here's root, and we have a tree that contains one element in it, 42. If we say delete 40, then the not contains will kick in, and we just don't do anything. If, however, we delete 42, then contains will be true. Right? It'll be true, so it'll continue. Our size is 1, so it's going to delete root, which is going to free that memory. That doesn't change the pointer. The value in root is still whatever memory address was there before. And so if we delete root, it frees the memory at that memory address. We then set root to null, which is going to have it point at 0 instead, essentially. And move the desk up a little bit. My pin's sitting here. Yeah, so root's now pointing at null, which is what our invariant is, right? We have an invariant that anytime we have an invariant that if the tree contains no data, root is null. Right? So that's good. Size should be decremented. Yep, size is down to 1, from 1 to 0, and we're done. That's it. So do you guys concur that this code is correct? What do you think? Looks good. Let's test it. It's not going to work if size isn't being set properly, right? Because with insert not doing size properly, it was just screwing everything up. Let's print. Okay, cool. Delete. Cool. Insert 1. Print. Delete 1. Print. Good. All right, so that code works correct. So now we got the situation where there's lots of things in a tree. And you can see this function is annoying. This is an annoying function, right? I don't like writing deletes for binary trees, kind of a pain. Okay. So we're doing this iteratively instead of recursively, just for funsies. So we're saying while temp. So what is temp? Okay. So we start off with temp equal to root, and we're creating a following pointer called parent. So let me explain what that means. So let's say that we have this tree here, and we're supposed to delete q. So we start off with temp. We start off with temp pointed here, and then the parent pointer is equal to null. And then is q bigger or less than f, everybody? Down here. Is q bigger or less? Do we move to the right? Do we move to the left? It is bigger, yeah. So temp is equal to temp points to right. So temp moves to here. And parent points to the artist formerly known as temp. So you see right here. So we're moving to the right. So parent is equal to temp. That's the one we were just on. And then temp is equal to temp points to right. And so what's going to happen is the parent pointer is going to follow behind temp. So however temp moves through the tree, parent's going to lag one behind, and that's very useful because if you delete like k here, you need L to point to G, right? So you need that parent pointer because we don't have one in our node. Our node class could have a parent pointer, but we don't. So as temp kind of moves through the tree, temp points to here, then temp points to here, then temp points to here. The parent pointer kind of hovers behind. So the parent pointer follows one behind at all times. So the parent pointer goes here, then finishes here. So parent's going to be there. And all that up. And temp is pointing to Q. Do you guys understand? So when we finish iterating through the loop and we found Q, parent is going to be set either to the person above us in the tree, or it's set to null, indicating that root is our parent, which we have to special case also. There's a lot of special cases. Okay. Parent is always what temp was previously. Precisely right, Max. Precisely right. Okay. You guys understand? So as temp goes down, parent just kind of follows it. It's a helicopter parent. So this part here, it's just saying if the value we're trying to delete, like 50 or whatever, is less than the value in the current node, we go down to the left. Otherwise, we go down to the right. That's standard binary tree stuff. And we keep iterating through the tree until we find the spot to delete. And when you find a person in a tree to delete, there are 3 possibilities. Maybe 4, maybe 5, maybe more. I don't know. The easiest possibility is that you're trying to delete a person with no kids. It's very easy to kill child-free nodes, right? It's like a leaf node, we call it, right? It's got no kids. It's very easy to delete them because all you have to do is delete it and set the pointer. See how we have a dangling pointer here now? We just set that pointer to be null. And you're done. It's 2 lines of code. Okay. So when you got a child-free node, you know, this guy would be temp here, this guy would be parent, parent points to right equals temp. The parent points to right is temp. So all you have to do is say parent points to right is null, delete temp, you're done. 2 lines of code. The only question is whether or not we're the right child or the left child right here. So if you've got no kids, you see that? If the left pointer is null and the right pointer is null, then maybe we should do left, then right. So if the left pointer is null and the right pointer is null, and we can make this null pointer. It's kind of trolling my students. 12 o'clock session, null pointer. Okay. So if temp's got no kids, his left pointer is null, his right pointer is null, then if we have a parent, that handles if you're root, because if you're root, and you got no kids, it's actually probably handled by the previous case. So you technically probably don't need this. It's a safety thing. Okay. So if the parent's data is less than our data, then we are the right child. The parent's right child is now null. Otherwise, the parent's left child is now null. We delete temp and we return. Do you guys understand this code? So basically, if we could have a couple scenarios, right, where we got like 100 here and 200 here. Temp is pointing here. Parent is pointing here. So we are, oh, not 220, sorry. So we're smaller than 100. And so there's 2 things we have to do. We have to free the memory and then set parent's left pointer to be null. Yeah, it's literally what we just talked about. So the only twist here is we have to know if are we the right child or are we the left child, right? So if the parent's data is smaller than us, we're the right child. If the parent's data is bigger than us, we're the left child. So we set the parent's pointer to be null. We delete the pointer. We're done. Okay. Then coming in here, add a return here because these are all going to cause seg faults. All of these are going to cause seg faults. Okay. So second test case, you have 1 child. You're trying to delete somebody that's got 1 kid. 2 income, 1 child household, right? So it's a little bit harder to kill a parent that's got kids, you know. That's why we send people off to war. They're typically single, unmarried, no kids. You know, it does happen that people have kids, and you can kill them, but it's just a little bit harder. Yeah. So let's say we've got, actually we just use this here. Let's say that we've got this guy. Make it a little bigger for you. You can read it. He's got a kid. Okay. So here's parent. Here's temp. And we're trying to delete temp. Temp's supposed to go away. So obviously we're going to need a delete temp in there somewhere, which frees the memory of 50. We're trying to delete 50 right here. There's one more line of code, though, that we need. So we know that temp's got a left child, so we have to do this special case. So what other line of code do we need there? Like we're definitely gonna at some point, either first or second, I don't know, we're gonna delete this. But now look at the pointers here. What needs to change? What's our other line of code we're missing? Temp is 30. So set temp to point here. That's not gonna. Temp's going away. We're returning from the function. All stack allocated variables are gonna go away. So now the child of former temp needs to connect to the parent. So you want 30 to point to 100? Is that how you want to connect it, Luke? Nah, can't do that. Because if we were to delete K, for example, Luke, if we're going to delete K here, we can't have G point to L. That doesn't work. It's not a tree anymore. Instead, what we need is for L to point to G. That's what we need to do. That's our missing line of code right here. Okay. So you're right. L and 100 now needs to connect to 30, but it's this way. So you have to say parents left equals temps left. So if we have a parent, so if temps left is not null, temps right is null. So if temps left is not null, temps right is null, then we are in a one-child scenario here, and it is the left child. So if we have a parent, parents left equals temp left. So parents left child is now this guy. All right, and otherwise root. So if we don't have a parent, that means we're deleting from the root in a scenario like this. 10, 5, and root is pointing at here. So we're deleting 10. We're erasing 10, then we need root to point to this guy. So root is equal to 10 points left right here. And then for the one right child, it's symmetrical. You guys see this? This is exactly symmetrical code. Should be good. Coding through symmetry, what do you guys think? It's the exact same code for the left and for the right. It's just I search and replace left with right, right with left. Okay, hard. Now the last one is deleting with two kids. All right, so let me open up a. This one involves the concept of a predecessor and a successor in a binary tree. So let's table our code for a second, and our ongoing British summertime. Oh, that's what BST stands for. British summertime. I'm kidding. Okay, so let's pull up a big one, big tree. Okay, so the notion of a predecessor and a successor. So a predecessor is the number that comes before us. Like if you're going to print out all the numbers in numerical order, this tree would print out 1, 5, 8, 10, 12, 15, 20, 22, 25, 28, 30, 36. So the predecessor for 25 is the number that comes before it numerically. So the predecessor for 25 is 22. And the successor is the number that comes after it. So the number that comes after 25 is 28. Okay? And so how do you get it? How do you find the number before you? How do you get a pointer to the number before you? How do you get a pointer to the number after you? The node holding the number after you in the tree. What's the yippee with an emoji? Hold on. What's the algorithm for it? Lamar, what do you think? How do I get the number after me, or the number before me? And this is something that you only need to worry about with a two-child scenario. Previous, isn't that a thing? Nope. This is not a linked list. We don't have a previous, we don't have a next. We got a left and a right. So and we do actually have a left and a right because we're deleting when we've got two kids. Okay. So let's see up here. 40. The previous guy is 38. The next is 45. So the predecessor for 40 is 38. The successor for 40 is 45. So how do we get the person before us or the person after us? Go right once and then left as many times as you can is exactly right, Burford. So if we want to get the number after 25, we say give us the smallest value in my right subtree. Of all the numbers bigger than me, find me the smallest one. And so of all the numbers bigger than me means the right subtree. Find the smallest one. The smallest number is always found in the bottom left corner. So in order to go and find the smallest number bigger than me, which is your successor, the smallest number bigger than me is the next number, is going to be 1 to the right and then left all the way down. If you are talking about the predecessor, it's the largest value in my left subtree is the predecessor. So out of all, let's look at 10. Out of all the people smaller than me, the biggest one is 8. So you go left 1 and then right all the way down. This is how you do it in code. So we're doing a predecessor here. We could have done a successor. And so what we do is we go 1 to the left, and then we say while we have a right child, go 1 to the right. And so this is going to stop when we have no right child. In other words, it's going to stop when we hit like 15 here or something like that. So if we're at 20, we go 1 to the left, and then we keep going to the right and 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 going to the right until we hit a node like 15 here that has no right child. Its right child is null. And so we have, again, the parent pointer is kind of like following it down like that. Now here's the magic. Here's the magic that makes deleting a... somebody's honking. Here's the magic that makes deleting from a two-child household work. Because the trouble with it is you can't just erase it. You know what I mean? Like you can't just erase L here. Because now T doesn't know whether to point to K or to S. And you're like, well, just have 3 pointers then. Who's honking? Can't do that, right? So the magic that makes deleting from a two-child pointer work is you get either the predecessor or you get the successor. So let's say the successor here. Q. Okay, and you swap the values. So L was there, Q was there. So now it's going to be Q up here, and it's going to be L here. And the reason why that works is because this does not break the invariant. If you replace a number that's about to be deleted with its successor, then all of the numbers left of it are still left of it. All the numbers right of it are still right of it in the right subtree. So you don't have to change. You don't have to change the left subtree at all. You don't have to change the right subtree at all, except for the node that you just swapped in, which is about to go away. Do you guys understand this trick? So if we were, let's just copy this into here. Paste. So real, what, where did? There we go. I guess that's okay. All right. So let's say we're deleting 10. Okay. Do you guys want to replace 10 with the successor or the predecessor? What do you guys feel like? Yeah. You swap them and then you delete the place where you swapped. Because the predecessor and successor are guaranteed not to have 2 kids. Why? So if you are trying to delete 10 and you swap it with 8, you find 8 by going left once and then you go right all the way down to the end until it doesn't have any right children. So you know it doesn't have any right children. It'll either have 0 children or 1 children. And so when you do this swap here, we can put the 8 here and notice that everybody left of it are still less than 8. Everybody to the right of it are greater than 8. You cannot break the loop, the class invariant this way. And then here, you've got 8 down here, and so you just set the parent pointer to be here. You set temp to be here, and then you recursively call delete. This gets deleted. This gets set to null, and you're good to go. So everything works out. Okay. So who's alive right now? Who's on chat right now? Give me a thumbs up if you guys are here. I got my coffee. And I know it's daylight savings day. I've been feeling jet laggy all day, even though I went to bed at like pretty early last night. All right. Santiago. Let's delete 36. Do you want to find the predecessor or the successor? What do you feel like? We can unmute you too. Santiago, you are not muted. Maybe you are muted. I don't know. So just pick one. Do you want to pick the predecessor or the successor? Which one do you want to go for? The number immediately before it in the numeric sequence or after it? Successor. Okay. So how do we get the successor? The successor is the smallest number larger than us. So where do we find larger numbers? In the left subtree or the right subtree? Where do we find numbers bigger than this? In the right subtree. Okay. So out of all these numbers here, the smallest number is always the one in the bottom left corner, right? Because this is smaller than this, which 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 is smaller than this. The very smallest person is the bottom left node. So if you go all the way down to the left, you go all the way down to the left until you hit, somebody that doesn't have, just have a null pointer as their left kid, what number is our successor for 36? What do you think? What is the smallest number bigger than us? Burford's coming in for the save. Maybe start early. What is the smallest number bigger than us? It's 38. Good. So we're going to come in here and we're going to swap the value of 38 and the value of 36 like that. And then we've got, not temp, sorry. We've got parent here. And we've got temp here. And then we call delete again, this time on 36. And so it will erase, this is the child-free edition, so it's just going to erase that memory and set this to 0. Okay. And no memory will remain of 36 ever being part of the Soviet Union. And that's the whole algorithm. Okay. So the trick to it, the tricky part about deleting from a node that has 2 kids in it is that you have to do the swap and then erase the place where you swap to. So the code looks something like this. So you go 1 to the left, we're doing predecessor this time. You go 1 to the left, then all the way to the right. The parent pointer is still trailing behind as we go. We swap the values. We set temp to point to the new guy. But then continue is going to jump back up to the top of the while loop here. And then it's going to immediately find it because temp's pointed at the person we're trying to delete. Still trying to delete 36. So after we deleted 36 and put a 38 up here, that's still our target. So it'll come up here and find it doesn't have any kids. It's got a parent. So the parent's left gets set to null, it deletes temp, and it returns. Okay. Exactly. Did you guys ever see Stalin Photoshop? It's like this guy here, right? It's like Stalin would edit photographs of people, and after this guy would be executed for betraying the Soviet Union, you just kind of airbrush him out of photos. Like, who's this guy? Never met him before in my life. Yeah. Photoshop was invented by Stalin to erase the existence of people he killed. Yeah. So you got 4 people, then it turns into 3 people, then it turns into 2 people, then it turns into just Stalin. Right? So. Boop. Yep. Alright. Ye old Photoshoppy. Alright. So, let's come to your homework assignment. And this one is a fun homework assignment. So I know you got Dungeon Delve going on. This one's not a programming assignment at all. So I'm just going to kick it out to you because it'll be due next Monday. And if you guys want, you can get a head start on it if you want. I'm going to be at a academic conference next Wednesday and Friday. So that'll be just posted video recordings for you guys to do asynchronously. Some quizzes on it. And then after that, spring break. And so we need to get this homework assignment here, which is called Black Box BST. Black Box BST. You need to get this one done by Monday, and then next Monday we will give you a mega assignment for you guys to do over the 2 weeks that you're on. Our favorite dictator. Exactly. So, yay, Kearney isn't frozen now. Good. Neat. All right. So for this homework assignment, this is like I'm not being sarcastic. This is actually a really fun homework assignment. A lot of students last year, I invented this one last year. They told me that this was actually their favorite homework assignment for the entire semester. So, not lying to you guys, this is actually a cool homework assignment, even though it's kind of mean in some ways. So what you have to do for this homework assignment is what we were just doing earlier in at the beginning of this recording here, which is try and figure out what's wrong with it without actually looking at the source code. This is why it's called black box debugging. Notice in what has been pushed out to you, there is no source code, right? So there's no main.cc. There's just a program. All right. And when you run the program, it will randomly pick between 50 trees for you to debug. So there are 50 different bugs, possible bugs. These are all different implementations of binary trees. I use inheritance, and I have a pure virtual tree abstract interface thing, and I will new trees of the different types and have a pointer, a unique pointer, and so I basically slot in between tree 00 and tree 49. And each one of the trees is different, and it is your job to, this is where the fun begins. This is exactly right. And so it's your job to figure out what's wrong with your trees. Notice, I did not start on tree 00. I started on tree 8. And my next tree is tree 10. And my next tree is tree 27. My next one's tree 34 and 49. And I'm done. Each person will get a random pick of 5 trees from the lot. They're sorted numerically. So I got 8, then I got 10, then 27, 34, 49. Okay. And so you can work on this homework assignment with a friend if you want, because guess what? If I work with somebody else, they're probably not going to have the same trees as me. So if, for example, I become Lamar here, and I go into black box BST and run it, you'll see Lamar has tree 2, tree 18, tree 25, 36, and 40, which is, none of them are the same as mine, right? So, if you want to work with one friend, don't work with everybody. But if you want to work with one friend on this, you can, because they're different. Probably you might share one by chance, So if I was Lamar, and then let me become Bean and see black box BST. Bean got 4. No. Then 17. Nope. 28. Nope. 31 and 42. Yeah. 42. Nice. Yeah, so if Bean and Lamar wanted to work together on this, it's fine because you have a completely different set of trees. Okay. Some of the bugs will be duplicates from each other. That's fine. Even expected. What kind of bugs are there? I don't know. Let's try running this. So we're on tree 4 right now. Let's just see what happens if we print the tree when it's empty. No segfault. Get the size when it's empty. No, that seems fine. The most difficult challenge is making friends. That's right. Computer science really is about the friends you make along the way. Okay, let's try searching. That worked fine. Deleting. Seems fine. No segfaults yet. And so what you need to do is you have to sit there and insert things into it, and search it, and delete it, and print it, and see if you can find out what's wrong with each one of the trees. Each one of the trees has 2 bugs in it. Okay? And so you're going to submit on Canvas. This is what's wrong with tree number 4. Tree number 4 has delete, doesn't work, or insert doesn't, or insert works, but it accepts duplicates. For example, that's one of the bugs. I don't know, let's see if that's the one here. Insert 10. Let's insert 10 a second time. Print it. No, that's not that one. What if we delete 10. Seemed to work. Search for 10. Yeah, so far, so good. Insert 20. Print. Insert -10. Print. Everything seems to be working so far. Insert 30. Insert 40. Insert 50. Get the size is 5. Grab the tree. We have 5 people in there. -10, 20, 30, 40, 50. Let's search for 50. False. Strange. What about searching for 20? That one worked. What about searching for -10? That one didn't work. Okay. So that's why you have to sit there and test them, and each one's different. Some of them are mean. Some of them are actually really mean. Like my favorite mean one is it flips a coin to decide if it's going to work or not. So you might just get lucky and just have it work. What? Yeah, it just flips a coin. So how do you debug that? I don't know. Figure it out. So that's simulating, though. In real life, you will have code that doesn't have random numbers in it, yet it sometimes crashes. Sometimes. And you're like, what? Why? You're not supposed to be random, Mr. Computer. You're supposed to do the same thing every time. And it's like, I know, but I'm still going to crash half the time. And so, yeah, you just keep hammering on it. That's the meanest one, Olson. That is definitely, when I was writing it, I just definitely had the troll face emoji going on with that one. One of the areas we have to find is like, oh, this tree has the flip a coin bug. Yeah, but the odds are only 1 out of 50. You'll get that one, so you're fine. You're fine. I've run this 100 times, but failed 55 times with the same input. Sure. Yeah, sure. Now you could type all this in by hand, right? Because it kind of gets annoying, like insert 10, insert 20. You could do it all by hand, sure. But remember how we were talking on Friday about Unix being important? Wouldn't it be cool if we could just like save all of those keystrokes into a file, like input file 1, and then we could do things like, I don't know, insert 20, insert 10, insert 40, insert 50, insert -10, and do that. The left arrow here means redirect the input so that instead of reading from the keyboard, it's reading from a file. And so all those keystrokes in that file get typed in. You can see here it inserted, hit print, and it printed out all the numbers. And then you can, and if you want to try the next tree, 6 goes to the next tree, right? And so then you can just feed it in that way and see, oh, look at that. Look at that. We got a problem here. Yeah. See that? Tree number 2, or whichever one it is, tree 17. Looks like we're not inserting right or something. And so what you can do is you can make a bunch of keystrokes that do build out a big tree, and then try printing it and deleting from it and stuff like that. And then you don't have to recreate that giant tree every time. Okay? So you can just put your keystrokes into here and save you a little bit of typing, or you could just like insert 10, insert 20, insert 30, insert 40. Select it. Run, right click, paste. And I built a tree. That works too. So having Notepad, like if you've got like insert and you've got like 30 inserts, put a Notepad, copy it, right click to paste, and buddy, good to go. Let's try it on here. Right click. Tree. Uh-oh. Tree 17, it's got problems. Tree 17's definitely got problems. So next tree, paste. Oh. When you select something, it copies it automatically. So it's better to put it in Notepad. Run it. Next tree. paste, print, size, seems fine, needs more investigation. So this is, what's that yellow text saying? Submit the above on Canvas with your secret code. So your secret code is this. Okay. And so each user on the system will have their own unique secret code. And this is how I know that you're submitting the trees that you're given instead of submitting somebody else's homework. It's an anti-plagiarism thing. So like right now I'm Bean, and Bean and Lamar are working together. He could just be like, well, tree 5's got this problem, and so you have to enter your secret code for you. And so I can know if you're doing your trees versus somebody else's trees, if that makes sense. Okay, so you have to copy and paste this secret code here into Canvas, and then you say tree 4 has a problem where it won't delete properly, from anywhere but the root, something like that. Tree 17's got a problem with inserting, apparently, Tree 28 has a problem with searching. So what are you submitting along with the secret code? So you're going to put your secret code in there, and then you are going to write a description of the bugs. There's 2 bugs in each one of these trees. And so don't type the same bug twice. Right? So like let's say there's a problem with inserting. So you insert 10, 20, 30, and you only got 10. That's a problem with insert, right? But some students will be like, well, it's also a problem with get size, because get size is only reporting 1 when there should be 3. I'm like, no, it's the same bug. It's just not inserting, and so some students try to like double dip, like, oh, well, there's a problem with search because search isn't finding 20 or 30. Yeah, it's because they didn't insert. You know what I mean? So don't double dip. But there's 2 distinct bugs in each one of the trees. So you're gonna write out a description of the error, what function you think is problematic, like which one, where is the bug? Is the bug in insert? Is the bug in erase? Is the bug in contains? Which function is the bug in? You got to guess, but it's an educated guess. It's not like it should be pretty obvious where the bug is. You know what I mean? Like if you're seg faulting when you do delete, it's in the delete function. Like it's not a problem with get size. And then you have to say, what you think the mistake is. Okay. And that's it for today, guys. So work on your code for Dungeon Delve. Get the bridges stuff going. And then, when you need a little refresher and amuse bouche, you want some fun. This is actually really fun homework assignment because some of them, like I said, some of the bugs are really easy, very straightforward, delete, seg faults, something like that. And then some of them are just like, it stops working after you go 3 levels down in the tree, it stops working. So it'll work just fine up here. You got to get down into the stratosphere, not the stratosphere, the lithosphere, in order to find the bugs, And so some of the bugs are like annoyingly difficult to find. But the whole thing shouldn't take you longer than an hour or 2 to do. So your bug answers have to be descriptive. Or you can say where the error lies. So what do you think the mistake is? Like, why do you think it's seg faulting, right? So, you have to say, for the function, you just say erase, insert, delete, whatever like that. You have to trigger it. You have to trigger the bug, give me an input that'll trigger the bug. And then, like, in English, like, what do you think the problem is? Okay? What do you think the problem is? You feel like you'll want to... Nah, it's fun. Like legitimately, it should be fun for you guys. So, if it's not fun, then, I don't know. It's fun. All right. So, yep. So there's no coding for this one. It's a completely black box debugging assignment. You're given no code. You write no code. You are simply, running end-to-end testing. You're handed a program. You're like, is this correct or not? And this is a really good exercise for you. We've been focusing a lot on debugging and input tests and things like that. And so, like I said, you can make your own input test for this and feed it into it to make the process go faster. So you're not manually typing 10, 20, 30, 40 every time you're trying something new. Yeah, probably won't start till Friday. It's fine. So yeah, if you're the Muad'Dib, it's easier because you can see into the past and the future. It's true. But I recommend staying off the spice, kids. It's addictive. Waters of life, like, just because, like, if your friends drank the waters of life, does that mean you should drink the waters of life? No. Just say no. Make Nancy Reagan proud. Is this a Dune? Yes, it is a Dune reference. Okay. Speaking of which, I should set my backdrop to be Dune. And wash, yeah, you know what spice is. Yeah, the spice melange, the geriatric spice. The spice extends life. The spice expands consciousness. The spice is vital to space travel. I was hoping that line would make it into the new one. I know I got a Dune background here somewhere. There we go. All right. There we go. So car tag, yeah. So this is like a control panel for an orthognopter, things like that. So it's kind of cool. It's not super obvious that this is Dune, but I like it. This is actually one of my favorite wallpapers. Arakeen, you can see here Arakeen, Kartag. Those are the two main cities on planet Dune. Yeah. It's a good movie. It's a good movie. I got the collectible popcorn. It's like this big. It's gargantuan. I don't know what I'll do with it, but everybody wanted one, so I'm like, all right, fear of missing out. I got to get the collectible drink, Dune 2 drink, and Dune 2 popcorn bucket. I have it. I do. I don't mean to brag, but it's just sitting next to my sliding door right now because I have no idea what to do with it now because it's a gargantuan popcorn bucket. The book is good too. Yeah, I definitely like the book. The books get weird later on, but Dune supposedly influenced a lot of movies. Yeah, Star Wars. In many ways, like Tatooine is very similar to Dune. The Jedi are basically Bene Gesserit, that kind of stuff. Use your bucket as a trash can. Do you have the top with a Shahaloud on it? No, I don't know. Give me $5 for it. Let me talk to my wife. I think she's got plans for it. We might turn it into like a plant or like grow like, I don't know, chilies or something in it. Dune invented giant worms. Yeah, that's true. Got this shirt. Nice. Yeah, that's it for today, guys. Thanks for coming out, and I'll see you guys on Wednesday. Peace.